continue on the topic that we began yesterday, namely convex hulls, two-dimensional convex hulls specifically. So, if you have any questions from yesterday, you can ask me. Okay. So, I think I just started on the second algorithm. Okay. So, let me recap. So, we decided that we are going to construct the upper hull and the lower hull separately, namely you consider the line joining the leftmost and the rightmost point, okay, and the part of the hull above is called the upper hull, the part of the hull below is called the lower hull, right. I just like to add one more definition. So, another definition for boundary points. So, I said yesterday boundary points are those points through which you can draw a tangent, right. So, a tangent is such that all the points of the given set should be on one side. So, that is what the tangent is. The entire convex hull should be on one side. There is another useful definition of boundary point which is often used when we design algorithms, and that is it's related to the definition of the convex hull in some sense, that so we said something about the entire segment connecting two points should be completely inside the set, and I called this the convex linear combination. Just recall, let's see, yeah, right. So, this is the definition that I am referring to, lambda p plus 1 minus lambda q. So, this is called a convex linear combination. So, boundary point is a point, okay, which actually cannot be expressed as a convex linear combination of 2 points in the convex hull. So, that is another alternate definition. So, a boundary point, okay, there is an alternate definition. A point P among the given set of points that cannot be expressed as a CLC, convex linear combination of 2 points in the convex hull. Okay. So, if your boundary looks like this is a boundary point, okay, this is a boundary point. None of these points, essentially I can't draw a segment, okay, that contains this point. So, if I try to draw a segment, okay, one point will be inside, the other point will be outside. So, this cannot, a boundary point cannot be expressed as a CLC of two distinct points. It can be expressed as a CLC of itself, you can, it is a trivial kind of combination, that point and itself, but it cannot be expressed as a CLC of any other point. Analogously, no point in the no point that is a CLC of two other points in convex hull of S is a boundary point. Okay. So, every such point is an interior point. So, any other point.
So, shouldn't be differentiating between the corner and the boundary points?
Okay. So, yeah, right. So, maybe I should say no. So, what is the distinction between corner and the boundary point?
The boundary, so if it is not a corner, but it is on the boundary.
Yeah. So this point, right? Yeah. So, maybe I should, boundary point, right. So, you are calling a point on this boundary, but then if you take a point on this boundary, it can be expressed as a linear combination of two other points, right. So, that is I think what you are saying. So, any other point can be expressed except these corner points. That's what it. Yeah, sure. So no point that is a is a boundary point. So okay, corner point. You want me to be more specific? Okay, corner point. Okay, thank you. So in other words, the moment we see that some point, okay, there is some point which is which can be expressed as a CLC of 2 points, we know that it cannot be a boundary point. It is no longer a candidate for a boundary point. So that is also another way these algorithms work, that the moment I find that some point is a convex linear combination of 2 points, it means that we can discard that from further consideration, right. So any point in the interior, see, you can so if suppose this is the convex hull, okay, any point which is in the interior, you can actually figure out that it is actually convex linear combination of 2 points, right. So very I can take any corner point, okay, join, draw the line, and it's going to intersect the boundary somewhere, okay, maybe here, okay. So this point is in the convex hull because it's in the convex linear combination of these 2 corner points, okay, this one and this one, and likewise this point is in the convex linear combination of this point and this point. Okay. So certainly any point in the interior, you can argue, is a CLC. In fact, there is a more general definition of convex linear combination, which is that so we are only looking at a convex linear combination of 2 points. You can actually extend the definition to a convex linear combination of more number of points. Okay. In other words, every point in the interior, okay, let me just write this. Okay. So a point P is a CLC of points, let's say Q1, Q2, Qk, if P is equal to lambda 1. So that's another alternate definition, that this points, it basically says, if you geometrically, it means that I have these points Q1, Q2, Q3 up to Qk, and this point P will be somewhere essentially in the interior of this, interior of the convex hull of these points. Actually, to be more precise, you can look at the convex hulls of Q1. So this is a definition. This is algebraic definition, and the geometric interpretation is that the point P is in the interior of the convex hull of Q1, Q2 up to Qk. That's what geometrically is the interpretation of that.
Also, every point inside that convex hull of Q1, Q2, Qk, that will be
A convex linear combination of the boundary points.
For some values of lambda 1, lambda 2, lambda k, right?
Right. Okay, so with this definition in place, let me go ahead.
Say that if a set of points is linearly independent, then the convex hull will comprise of all those points as the corner points.
Linearly independent. See, in 2 dimensions, how many linearly independent points can you get?
Not linearly independent, like they cannot be expressed as a convex combination of other points.
No, so the boundary, the corner points of the convex hull, they are certainly not convex linear combination of the remaining points. So you can have any number of points. I give you 100 points, and all those points can be corner points of the convex hull of those points, and therefore all those points cannot be expressed as a convex linear combination of the other points.
Like I'm saying like vice versa. So if I have a set of linear combination of
Then
them,
all of them are boundary points,
then all of them become,
corner points or whatever. Yeah.
then all of them become corner points.
Right.
So I have the convex hull.
Right.
without complete-
Right. So that's the algebraic way of expressing it. Okay. Okay. So going back to this. Okay, one more point I should make. This was there was a question yesterday at the end of the lecture that when I separated out the upper hull and the lower hull, why shouldn't the upper hull and the lower hull have any kind of interaction? Right, there was one question asked, and I gave some sort of an answer, but let me elaborate on that a little more, because this also happens to be one of the sort of motivating applications of convex hulls, not only in 2 dimensions but in higher dimensions also. And that application is that if I have given a set of points, well, not one set of points, let us say 2 sets of points. Okay. And let me use 2 different colors for that. Now, I want to ask the following question, that can we draw a line that separates the 2 sets of points, namely the black and red.
If the convex hulls are separated.
Exactly. So, it turns out that yes, and if and only if the convex hulls of the 2 sets are disjoint. But so in this particular case, of course, if you look at the red point, this is the convex hull of the red convex hull, right, and the so there is an intersection of the convex hull. So there is no way that you can actually separate them, right, and analogously, if the 2 convex hulls are disjoint, okay, then you can have a linear. This is basically a linear separability of point sets, right? And it's a very important primitive, for many things, including even learning. Okay, so and it's a very hard problem to solve in higher dimension. Okay, so in 2 dimensions, we can construct the convex hulls in polynomial time or whatever, and find out whether they intersect or not, etc. All that can be done here.
Do we necessarily do find the convex hull? Do we have to find the
No. So this is the only characterization that we know of.
So is there any better thing?
Well, there is nothing as clean as this. Okay. So the question here is that do we necessarily have to construct the convex hulls? Well, if it were so, that then we have kind of almost a lower bound argument that if the convex hulls are very hard to construct in higher dimension, then there cannot be any efficient algorithm. But there is no such result, but this is the cleanest formulation that we have of the problem, that is all. So, it is not known how to do this efficiently in high dimensions. Right? Dimensions mean arbitrary dimensions, it is not just 2 or 3 or 4, but let us say dimension d. Do we have an algorithm that runs polynomial in number of points n and d? So, that is not known. Okay, so when you talk about the upper and the lower hull, essentially what you are doing, you are actually looking at this convex hull, the final convex hull, okay, and we are essentially linearly separating them out. Okay. So, if we have this linear kind of separation, this is the line that we are using to separate them out, leftmost and the rightmost point, okay, which means that the entire upper hull lies upwards of this line, the entire lower hull lies below this line, okay, and you are talking about this convex hull including these 2 endpoints, and this convex hull including these 2 points. So, there is no other intersection other than this line. So, they cannot have any kind of interference. So, we can construct them independently. because they are actually linearly separate. We have by construction. So, you take any convex hull, not just this is take any convex hull. Okay, I can draw any line, and this part and this part, they are already linearly separated. So, they are not going to interfere with each other when we do the construction. So, the construction can be done independently. Right. So, I just wanted to make this point that this is one of the sort of more important applications of convex hulls. This notion of linear separability. Okay, so now let us proceed with constructing the upper hull. Okay. The first thing we are going to do is rotate the axis. Okay, so, this line that we have, the separating line, let us assume that it is the horizontal line. This is my x axis kind of, just to sort of make it easier to visualize. Okay. And we have these points above this line. Okay. So, you know that even if I rotate the axis, the convex hull remains the same, right, it is invariant. Right. So, we have some points. The first thing that we are going to do is look at the sorted order of these points. So, this is the L, this is R, okay, and I am going to join the points in the sorted order along x axis. Right. So, I have some kind of a singularity which I do not like. I have been telling you that I do not want 2 points to have the same, just that it is cumbersome to explain, that is all. So, actually sorry. So, I have joined these points in what is called a monotone chain, right. This chain, if you walk along the chain, it is always going to move in the direction of the positive x axis. Okay. So, this is a monotone chain. Right. Now, this is not necessarily a convex chain. Okay. We want to now convert this or transform this into a convex chain, which means that some points will not belong to the convex hull, and those are points that we want to identify. Right. Okay, so, we start walking along this chain. Right. So, we start walking along this chain, okay, and the property of the convex chain is that it should always sort of, if you are walking from towards in the positive x direction, it should always basically turn towards the right. Right. So, we walk, okay, and we make a right turn, that is fine. Okay. Then we come to this point, let me number them, okay, before I lose them. So, when I come to point 1, I make a right turn, which is unacceptable, because it is by definition convex chains should be right turning. But the moment I reach point 2 and I try to go to 3, I have a left turn between the points 1, 2 and 3, right. So, I have made a left turn here, which means that this point should not be on the convex hull. And can you explain this on the basis of the definitions that we have done just recently? Why should not point 2 be on the convex hull?
Can be expressed as a convex combination of 1 and 2.
No,
Not 1 and 2.
no. Yes, triangle area is what we are using to figure out whether it is left turn or right turn. My question is why, what is the logic or what is the reason that we can forget about point 2?
Because it's and on that the angle that is there is more than 180. take a point on this x axis and it can be expressed as a convex combination of that point and 1.
Yes, that's certainly I think one of the answers. So, what is being said here is that this so let me use another color. So, you look at okay. So, what is being said here is that this point and you extend it, this point is on the boundary and therefore 2 is a convex linear combination of that. Yes.
So, I mean, you said in the convex angle, all points will be one side, right? 1, 2 divides 3 and another point.
Yeah, sure. So, that's another good argument that okay. So, you are saying that I cannot draw a line through point 2 such that all points will be on one side. That is the other observation being made. So, if it is a left turn, there is no way that I can draw a line through 2 such that all points will be to one side of the line. Okay. Another thing I can see is that well, I mean this is a good enough proof, but you can look at what is the relation between 1, 2 and 3. So, 1 and 3, okay, this so this segment should be in the convex hull. So, any point on this boundary should be on the convex hull. So, this thing again 2 is a convex linear combination of these 2 points. Okay. So, again it basically drops out.
So, we can also say that at 2 it is making an angle more than 180 degrees.
Right. So, all those reasonings are fine. So, yes, I mean that another thing I forgot to mention that these kind of angles where okay. So, you look at the interior of a convex hull, you look at these angles, okay. These angles must be less than pi and this is called a convex angle. Less than pi is a convex angle and greater than pi is called a reflex angle. Okay. So, clearly any time we make a left turn, this is going to be a reflex angle and therefore, that cannot be a point on the boundary of the hull. Right. So, there are many reasonings due to which left turn basically means that we have lost that point. Right. So, we get rid of that point and so we can say that 2 cannot be on the hull. Okay. So, I am going to take out 2 okay, and now change my walk to go to 3 directly from 1. Right. So, now again L 1 3 these 3 points form a right turn. Okay. So, there is nothing wrong with it. Okay. So, we proceed further. Okay. We again at 1 3 4 again it is a right turn, fine. So, that is also okay, and then again we have a problem from 3 4 5 it becomes a left turn, right. The moment it becomes a left turn, it means that I cannot consider 4. So, 4 goes out of consideration. Right. Then I have I should go to 5 directly from 3. Okay. So, we continue like this and then again it turns out to be a left turn. So, in the next when we go to 6 even 5 should drop out and we should go to 6. Okay. Now, it is not clear whether 1 3 6 is a right turn or not. It is let me refer to the third umpire and let us say it is a benefit of doubt, it is a right turn. All right. Fine, but 3 6 7 makes a left turn again. So, that means that okay, that is gone. Right. All right. Now, again it is referred to the third umpire. Okay. So, my diagram is such that, and this time let us say the umpire makes a decision this is a left turn. Okay. So, which means that not only we lost 6, okay, we should also lose 3 because 1 3 7 or if you look backward 7 3 1. Okay. So, there is a problem at 3. Okay. So, just to make it look better, let me raise the level of 7 a little bit more. Okay, let us take 7 to be here and then I think things fall in place. Okay, now it looks like more like a left turn. So, there is a left turn from at 3 from 1 3 7. Okay. So, we cannot have this chain. So, we should also now forget about 3, okay, which means that I should go to 7 directly from 1. Right. So, what this illustrates is that if there is a left turn at 1, so at some point, okay, that point gets dropped, okay, but as a result of that we may also lose some of the preceding points. Okay. Let me make this example more pronounced. Okay. So, we had a situation, let us say, where it was like this. Okay. So, these were the points where we make these right turns, suddenly we have a point here. Okay. Of course, we lose this goes out. Okay. So, we should consider this boundary. Now, this is a left turn again. So, this goes out. Okay. This is knocked out, same thing, this is still a left turn, this is knocked out. Okay. So, you can see it could actually have a chain reaction where a lot of things can get knocked out, due to just consideration of a new point. Okay. Okay. Fine. So, even if all this happens, finally what we get, at the end of, after walking and reaching R, is a chain that is necessarily a right turning chain. Okay. So, in this case we basically end up with this. Right. So, we end up with this. This is always a rightward right turning chain. So, all internal angles are convex angles, and we are satisfied with this. Any point that is knocked out once can never be a part of the convex hull, because it is already a CLC of some point gone, right.
So, but whenever you are making a left turn, you are potentially now have to check for all.
Right. So, algorithmically we will see what to do, but we are not yet reached a stage where I am trying to count the number of operations. All I am saying is that, but it is nice ordered structure, right. When we go back, we are going back by one step. We do not have to jump and find out some we just reverse basically from there. We do not have to check a random point. Okay. We just reverse, and we keep reversing till we find the chain is right turning, and prior to that also it is right turning. So, the entire thing should be right turning. Okay. In other words, what we are doing here is some kind of an inductive argument, that if we have considered up to point I, okay, we will have a convex chain up to point I. So, that's basically what we are doing. Right. Okay. Now, let us look at the time complexity of the whole thing. What is it that we are doing? So, we had sorted. Okay. So, running time. So, sorting is going to cost us something. Again, we are, let us say there are n points above, okay, n log n. Next, we are doing this scan, so we are walking, and sometimes deleting points, sometimes adding another point to the chain. Okay. So, constructing the convex chain by adding the next point or deleting how many points? Yeah. At most what is at the ith stage we are removing I minus 1 points at most, something like that. So, what is the running time? Okay. So, you did not sum up the I, right? You did not sum up the I, you did something smarter than that. Say a point can be deleted only once, right. And what is the data structure that will support it? Yeah. So, you just stack up the points, and when you have to retrace, it is the last in first out. So, you have to reverse, and reversing is very easy in the stack. Any other kind of data structure also, we have the right pointers, you can do it. So, there is stack or some kind of linked list with the right pointers, anything is fine, all right. So, overall then a point, what we are saying is that since a point can be added or deleted once using a stack So, running time here is basically number of left turn right turn tests, right. So, this procedure or this particular algorithm goes under the name of Graham scan. The total running time is the sorting time, whatever it takes, plus linear time.
So, determinant computation has some multiplications and
Right. So, but it is a constant size determinant, right. It is a 3 by 3 determinant. So, that is subsumed within the big O notation. So, whatever time it takes, it takes about 3-4 multiplications, 3-4 additions. So, that constant will have that constant 3 or 4 or 5 or 10, whatever. So, we are ignoring the constants. So, now you have an order n log n algorithm as opposed to an n times h algorithm for that the simple one where we sort of pulled a rope around all the points. Which is better? Of course, in the worst case this is better. But if you have very few points in the convex hull, namely you have many, you have let us say about constant points, then the previous algorithm is still somewhat better. So, although we have a faster algorithm, there are some cases where the previous algorithm could be better. Okay. We will address that. Okay, that's an important issue. But even prior to that, again our same question, can we do better?
So, I have a question
Mhm.
before the word one. So, why did you then in the alpha then you are going to do some divide and conquer? Otherwise, you could have done this whole procedure could have been done on the whole thing.
Yes, yes. I mean, when you do the implementation, you can do it all together, upper and lower hull, except what you need to do is instead of doing, I avoided what is called a polar sorting. Okay, so I would have to actually sort, with respect to angles, but then again, that we don't have to compute angles. We can do it everything with respect to left and right turns. Yeah, it's just that this is easier to explain and see.
Because Graham scan generally is
Yeah,
delivered
yeah.
as this polar.
Yeah,
thing
yeah,
like
yeah. Exactly. I can actually run the whole thing at once. All I need to do is identify a point inside the convex hull. I want to sort everything inside the convex. Just okay, since the point has been raised, so you have these points given to us. Okay, I need to identify some point will be strictly inside the convex hull. Okay, maybe this. Okay, and I am going to do my sorting or whatever. I have to. I will. So my monotone chain will be essentially this, which is what I have to convert to a convex chain. So, how do you find a point inside the hull? Two is not a good thing. Take any 3 points, and any convex linear combination of 3 points must be strictly inside the convex hull.
But here also you can start with the leftmost point, right? I mean, just start with the leftmost point.
No. So, it will not work. So, this is I have actually, if you look at the homework problems, I have given one as a problem that you have to do this kind of polar sorting. There are some complication otherwise. You may end up getting what is called a self-intersecting chain. This is a problem. So, you may take right turns, but you may take right turns like this. So, you have to avoid that. Okay. The right turn is not always necessarily good. It is working because we are starting with a monotone chain. All right. So, can we do better? Are we satisfied with n log n, or can we do better? So, let me give one construction. I think that will convince you, at least it will partially convince you about something. So, let us consider something like a parabola. let me consider a set of points given to me, okay, which are just points, there is just values. Okay. So, these are actually the numbers given to me. And not necessarily in this ordered fashion. It's given to me in some oddball fashion, x1, x5, x2, xi, xn, x20, so on and so forth. So, I have given some points. Okay. What I am going to do is I will project these points on this parabola. Actually, not project, but I should use the word lift. Okay. So, I am lifting these points by one dimension. So, a point x I is getting mapped to x I comma x I square. Okay. So, given a point set, given S equal to x1, x2 to xn, okay, I am defining S prime as a two dimensional set of points x1, x1 square, x2, x2 square, etc. Now, I construct the convex hull of S prime. What is the convex hull of S prime? All these points. What is the convex hull of this? So, all the points will be corner points. Are you convinced about this? All the points will be necessarily corner points. And if our assumption or convention is that a convex hull algorithm should produce the points in whatever clockwise or counterclockwise fashion, then I can recover from the convex hull the sorted set of the points. Okay. So, gives us an ordered set okay. So, either it will be like this or it could be like this, either way is fine. So that we can sort S using this ordering, since all points are on the boundary. So, we have essentially shown that sorting is linear time reducible to convex hull. Sorting of S is reducible to convex hull of S prime, and therefore, convex hull must have a lower bound of sorting. Otherwise, I could reduce sorting to convex hull and then sort it faster than the lower bound for sorting, which cannot be, right. So, the lower bound for sorting must be also applicable to the lower bound of convex hull.
So, what are these points exercise?
These are the points I have been given that I wanted to sort.
Earlier in 2 dimension it had.
No, it is not a two dimensional set of points. I have reduced the problem of sorting. So, I have been given this points x1, x2 up to xn, which I am supposed to sort. I have shown you how to sort using a convex hull algorithm. and therefore, convex hull cannot be constructed faster than the lower bound for sorting, that is all. So, when I reduce problem P 1 to P 2, so whenever I can reduce problem P 1 to P 2, okay, the lower bound of P 1 is applicable to P 2, okay, and the upper bound of P 2 is applicable to P 1. Of course, this must also happen in some efficient time. So, I have not mentioning this. So, hopefully, you are familiar with the reducibility in time f n or whatever. So, this f of n cannot be too large, it has to be. So, if this was not order n reducible, but let us say order n log n reducible, it did not mean a thing.
But sir, should be improvable because in terms of h, because if h is some order 1, then our algorithm should be.
Right. So, yes, will come back to that. We will come back to that. But what this problem, what this proof shows, it is a very simple proof, but this proof establishes something. Okay, let me summarize what this proof establishes first. So, this proof claims that so this proof or let us say some observation about the proof, let us say. One, okay. We are assuming that convex hull algorithm must output ordered set of corner vertices. If I did not have this constraint, I suppose I was only interested instead of outputting the corner points in any order. Suppose my convex hull algorithm was not required to produce these vertices in counterclockwise or clockwise order, but okay, just here is a set of points as tell me what are the corner points. If my convex hull problem was specified like that, this lower bound will not hold. Okay. And number 2, what was just observed here is that so, I could be interested in an algorithm where I only have to identify which are the corner points. I do not have to output them in any given ordering. Okay. If I no, so then the previous reduction does not hold, because I have to assume that the convex hull gives us an ordered set of boundary points. So, that from there I can reconstruct the sorted set. If the points, the output points were not to be produced in any sorted order, then I cannot reconstruct the convex hull from there. Okay, sorry, the sorted points from there. So the proof uses that strong assumption that the output of the convex hull. So, for most algorithms for convex hull, it produces them in sorted order, but then someone may have a different specification. Okay, that is all it is. So, most natural algorithms you will design will produce them in sorted order, and therefore, this proof goes through. But then theoretically, why do we always want the points to be in sorted order? I may be only interested to know what are the corner points, and therefore, then in that case this reduction does not hold. Okay. And number 2, if all points are not on the boundary, I only h, where let us say h is much smaller than n, again this lower bound does not give us anything. To the contrary, we have already seen we have an algorithm that works in n times h time, we have an algorithm that works in n log n time, and they are incomparable depending on the size of the output. If the output size is very small, one is better, if the output size is large, the other one is better, and we only know that if the output size is large, then n log n is optimal if my convex hull is required to produce the points in the sorted order. So, I will address this one again later. I will postpone this discussion when I get into more formal models of lower bounds. Okay. So, about point 2, okay, it basically leaves or gives us hope, or whatever you call it, or we have to break our heads again to figure out if we can have something better than n log n. Okay. N h and n log n are not comparable. Okay. We want something that will behave whatever you call it, optimally or whatever, for whatever the output size is. You remember what we did for the 2-dimensional maximal? What did we get eventually? N log h, right? So, that would be a good guess. If we can get an algorithm that is n log h, okay. So, the question I am raising here is this: how about n log h? Okay. So, can we get an algorithm that works in n log h? Because if it does, okay, then this would actually subsume both the cases, n h and n log n, because when h is large, then it will be no more than n log n, and when h is small, then again it will be better than n times h. However, as I said, the optimality of this again will be left. I am not going to address it at this point. So, we will just try to see if we can obtain an algorithm that can that for which the running time is about n log h.
Another question in that point 2. I mean, suppose if all points are not on the boundary, only each of them, so and assume that your convex algorithm is required to give them in a sorted order. So, that means the lower bound that is coming from that above construction is order n is required for you have to scan all the points, obviously.
No, but that only give you h log h bound,
H
right?
log h. So, it is only n plus h log h, that is the lower bound that you are getting.
Yeah,
H
yeah.
log h, can you determine that lower bound?
Yeah, that is what I am saying. So, this both for maximal points and this one, it turns out that you can actually prove this sort of a lower bound n log h. Right? So, this is a tight bound actually, but that discussion we will have to wait. So, let us first try to design something better. Okay. I will give you the idea and then we will carry on next time. Okay. So, historically, there was a very very well known algorithm for convex hulls, and that is a very simple idea. What it does is it identifies the leftmost point. Again, let us look at only upper hulls. Okay. Rightmost point, okay. And then what it does is, so we are given other points. It finds out the point that is furthest from this line passing through LR. Okay. In other words, if you translate, you think about parallelly translating the line LR, what is the furthest? In terms of perpendicular distance, let us say. So, you can find out the distance from this point from this line, right, again using some formula of the analytical geometry. Okay. And suppose this is the furthest point in this case. Right. So, then this point will necessarily be on the convex hull. Okay. That is known, fine, that is nothing new. Then what you do subsequently is that look at this triangle. Any point in the triangle will not be on the convex hull, okay. Gone. Okay. So, these points are all gone. So, what you are left with are points here and points here. So, what you can do now is try to construct the recursively, try to construct the convex hull of this side, or let me use another. Okay, and construct recursively the convex hull on this side. Again, this can be simply pasted, because that's the separating boundary. And you keep repeating this. It's a very simple thing. You just find this leftmost, rightmost point, draw the line, find the point furthest from there, and throw out all the points from in the triangle. You can modify this by figuring out some trapezoid and throwing out all the points from within, but this is, as I am saying, historically this was identified as a very simple procedure for finding convex hulls of point sets. Okay. And this goes under the name of quick hull. So, quick hull was discovered even before this Graham scan etc. were discovered. Now, what do you think is should be the running time of quick hull, this kind of quick hull? Average over what? All possible what? Yes. So, no. So, how would you even why are you even thinking about averaging? Because you don't even know how to express that average. Till now, we are never talking about how the point sets are distributed, right? Point sets, how point sets are distributed, we don't even have a measure or notion of that yet. Right? So, let us not, bring that into NH. Okay. No, in the worst case, what will be the running time? Let's even forget about H.
The triangle is formed, there will be no point.
N square. Huh?
No point in that thing. So, at least n minus 3 are still outside. So, at each iteration.
No, but then you can also be dividing it very nicely, right? So, why is it called quick hull? Can you make a guess? Why is it called quick hull? Yeah, it's very related to quick sort, right? What do you do in a quick sort? You identify a splitter, okay, and divide the points into two sets and sort them recursively, and that's your quick sort. Okay. Here it is called quick hull because it reminds you of that. Reminds one of that. I have basically now have two sub problems where I am recursively sorting and doing. So, sometimes people say that quick sort has a running time of n square in the worst case. Why do people say that? Because if the splitter point or the pivot point is very skewed to one end, you are not actually doing much justice to dividing the problem. So, quick sort works very nicely when the point sets are more or less equally divided, okay, and that can be actually almost guaranteed by if you choose a splitter at random. Okay. Here, by the way, we are not choosing anything at random. We can't choose anything at random. Everything is defined on the basis of the point set. Here is the left point, here is the right point, and here is the point that is furthest from this line. So, there is nothing probabilistic or randomized about this. Okay. So, we can't even ensure like we do in quick sort by picking the pivot element at random. Well, in this description there cannot be any randomness, right? You agree? Then you have to prove certain properties about it, right? If you pick a point at random, how is going to behave, how is going to split up, we have no idea. So, it is not clear. She is just saying that we just pick a point at random. How we do it, we will have to think about it, but somehow randomness is some kind of magic, that will work. Okay. We will come to that. So, I will show you that it does work as magic also, but not in a very straightforward manner. Here, you have the same thing again problem that I can have a situation where all the points will be on one side, okay, and therefore, I am not going to divide the problem into doing any justice about fairly dividing the problem. So, it run into the same problem of when you do not use randomized quick sort, you may have the problem. So, this has the same problem. But let me just make this one modification, and again the solution is to use some kind of randomness, but I will, okay, so I think we are out of time today. I will take it up next time.